Welcome back, everyone. Today we are going to look at some moon facts. So we're going to talk a little bit about the moon and about how the moon was formed and some tide stuff. So here we go. First fact about a moon. A moon is a natural satellite orbiting a non-stellar celestial object. So it's kind of a convoluted definition. And natural satellite makes sense. It's not something man-made. It's something natural. But the non-stellar. So if it's orbiting a stellar object like the sun or a star, then it's not considered a moon. It's called something else. But you can have moons around planets. You can have moons around comets. You can have moons around asteroids. So you can have moons around other things. It doesn't have to be a planet, but it needs to be something that's not a star. As we learned from our reading assignment, it was most likely formed when a planet-sized object named Theia struck the Earth, ejecting parts of the Earth's crust, which then later reformed in a gravity to make the moon. So that's the most commonly held theory at the moment. It's about a quarter the size of the Earth. However, it is less dense than the Earth. So because it has less mass and it's less dense, the gravity is actually less. It's 1/6 of Earth. There is no atmosphere, so you cannot breathe on the moon, which is why astronauts wear spacesuits on the moon. And the temperature has wild swings from negative 310 degrees to 265 degrees. So people were wondering, like, if the temperature is 265 degrees, wouldn't the astronauts be cooking? Isn't it like an oven? And the answer is no. The reason is, in an oven, the reason things cook in an oven is because all of the air inside the oven is at that temperature. But on the moon, there is no air. So the empty space around the astronauts, it's not hot because there's nothing there to be hot. So in those 265 degrees, they're not really cooking. Their suits are also made of white, reflective materials, so that a lot of the cosmic radiation and the radiation from the sun that hits them is being reflected. So it's not being absorbed by them, making them warmer. Most of it is reflecting, so it's keeping them cool. So the moon orbits the Earth, and the moon also is rotating. So if this is the Earth, the moon is spinning, and it's spinning around like the Earth spins around the sun. So the moon spins once 27.3 days. So that would be like one Earth day or one moon day would take 27.3 Earth days. So it takes 27 days on Earth for the moon to spin one time around. The orbit is also 27.3 days. So it takes 27.3 days to spin once, and it takes 27.3 days to go around. So it's spinning like this, right? But it's 27 days to go around once, and it's 27 days to go around once. And it's called tidal locking. And this is why we only see one side of the moon, is because it takes 1 day to go around, and it takes 27.3 days to go around, and it takes 27.3 days to go around. And we'll kind of see. I know I'm not explaining that well, but let me get some graphics up, and that should make more sense. Most moons are tidally locked, so most moons do behave this way. So let's take a look. So we do have this. This is happening 27.3 days. This is the rotation, and then the orbit is 27.3 days too. If it did not rotate, and the moon was here, and the moon was only orbiting, we would see different sides of the moon. Right now, we'd be seeing my thumb side of the moon, and as the moon rotated, now we're seeing the back side of the moon, and then now we're seeing the thumb side of the moon again. So it's actually rotating but it's rotating so that the thumb side of the moon is always facing. So they're just synced. The rotation and the orbits are synced. So here's a short video that kind of explains it, probably better than I just did. Let's take a look.
In 1959, the Soviet spacecraft Luna 3 beamed back images of something Earthlings had never before seen, the far side of the moon. We always see the same old side of the moon because the moon rotates exactly once on its axis each time it orbits Earth. If it weren't spinning at all, we'd get at least one 360-degree view of its surface with each lap. If it were spinning twice as fast, we'd also see the moon's entire surface more than once per orbit. But instead, our moon's motions, like the spin and orbit of most other moons in our solar system, are remarkably in perfect sync. This wasn't always the case. Our best guess is that our own moon formed due to a massive asteroid impact, and its initial spin and dizzying 10-hour orbit were almost certainly not in sync with each other, though we don't know which was faster. At such close range, Earth's gravity deformed the moon into a slight oval, with one of its bulges facing Earth. Those bulges quickly swung out of alignment thanks to the moon's asynchronous spin and orbit, but Earth's gravity continually squeezed them back again. What's more, this gravitational tugging would have influenced the moon's rotation rate. If it was spinning more than once per orbit, Earth would pull at a slight angle against the moon's direction of rotation, slowing its spin. If the moon was spinning less than once per orbit, Earth would have pulled the other way, speeding its rotation. Whatever the case, it took just 1,000 years for the Earth's pull to adjust the moon's spin enough that one rotation of the moon corresponded to one trip around the Earth, leaving one side forever locked facing away. We do end up seeing some of that far side because the moon's elliptical orbit gives us peaks beyond its average eastern and western horizons, and its tilted axis causes moon seasons, revealing more of the lunar north or south poles. But those glimpses only add up to an extra 9%, leaving 41% of the moon hidden from Earth. Satellites, starting with Luna 3, have allowed us to map the rest, but it's safe to say that our relationship with the moon is still pretty one-sided. I'd like to say a big thanks.
Okay. Yeah, so the moon is totally locked, and that basically just means we only see the same side of the moon because the orbital and the speed that it orbits is the same as the speed that it rotates. Phases of the moon. We have different phases of the moon. So the phases of the moon, it corresponds to the amount of light we can see shining on the moon. So if we have sunlight coming in from the right, the light is always hitting half of the moon, but we don't always see that. So like if you look here, half of the moon is lit up, half the moon is lit up, half the moon is lit up on all sides, right? Because the sun's coming in from the right and it's going to hit this side. However, when we're here, it's lighting up this half of the moon, but from our viewpoint, we can't see any of it lit up. So what we see is this part. It looks like a new moon. Conversely, on this side, this half of the moon is lit up, and from our viewpoint, we see all of that's lit up, so we see a full moon. For the quarters, this side of the moon is lit up like it always is, and that's what we see. For this part, this half of the moon is lit up, but from our viewpoint, we only see a sliver of it. We can't see the rest of the part that's lit up. So half of the moon is always lit up from the sun, but we see these different phases because of our angle, our viewpoint. We only see part of the lit up portion. And the phases start with the new moon, and it goes to it waxes to full. So we have waxing crescent, first quarter, and then waxing gibbous. And then it wanes and it goes away and it goes backwards. So we have a waning gibbous, a quarter, and then a waning crescent. So to write that down in words, half the moon is always lit up by the sun. We have phases because of our angle viewing. We only see the lit up part of the time. These phases are either waxing or waning. There are 8 phases, So starting with the new moon, and then we have the waxing and the quarter and the waxing. So waxing crescent, quarter, waxing gibbous. Just kind of keep going around. Oh, here they are. New moon, waxing crescent, first quarter, waxing gibbous. And then we have the full moon, and then the waning gibbous, third quarter, and waning crescent. So here's a woman doing a demonstration that kind of shows this in better detail.
Hi, my name is Emily Morgan, and I'm the author of Next Time You See the Moon from NSTA Kids. And I'd like to share a simple activity with you that can help you understand why the moon looks different at different times throughout the month. Why sometimes it looks like a banana, and other times it looks like half of a circle, and other times it looks like a big round ball. Well, to do this activity, you only need 4 simple things. You need a lamp with the shade removed, a white foam ball, a pencil, and a dark room. The darker the room, the better. Now in this model, the lamp is going to represent the sun, and of course the white foam ball is going to represent the moon, and your head is going to represent the earth. So let me show you how this works. We know that the moon orbits the earth. So in this model, I'm going to get the moon, the foam ball, to orbit the earth, my head. Notice that no matter where the moon is in its orbit, half of it is always lit up by the sun. But when the moon is in this position, I can't see any of the lighted side of the moon from Earth, my head. From this angle, you can see what I am seeing from Earth. We call this new moon. When it's new moon, we look up at the sky and we can't see the moon. It's there, but the side that's reflecting sunlight is away from us. Now, as I slowly make the moon orbit to my left, I can begin to see a tiny sliver of that lighted side. We call that a crescent moon. As the moon keeps orbiting, we can see more and more of that lighted side. We see half of the lighted half, which is a quarter moon. In this case, a first quarter moon. As we keep orbiting, we see almost the whole lighted side. We call that a gibbous moon. Then, when we can see the entire lighted half of the moon, that's a full moon. As the moon continues in its orbit, we begin to see less and less of that lighted side. We're back to a gibbous moon, but this time the light is on the opposite side. Then another quarter moon, last quarter moon to be exact. Another crescent, and finally back to new moon. And the cycle begins again.
Okay. Let's move on to the tides. We know that the Earth pulls on the moon, and we know the Earth pulls on the moon, which causes the moon to orbit the Earth. We also know that the moon pulls on the Earth, which causes the tides. I think we already know that. Do you think that the moon pulls on the Earth with a stronger force, a weaker force, or an equal force that the Earth pulls on the moon with? What do you think? The answer is equal forces. Forces are equal. It is Newton's third law. So for every action, there's an equal and opposite reaction, so they pull equally. So the Earth is pulling the moon, and it's keeping the moon in orbit. The moon is pulling the Earth, which causes the tides, and those forces are the same. There's a bigger effect on the moon because the moon is smaller, but the forces are equal. Forces are the same. It just has a bigger effect on the smaller object. So we experience tides twice a day. So here, if we have the moon, it makes sense that it pulls and forms a bulge on this side. However, there's actually two bulges. We actually have a bulge on both sides, and it's due because of the gravitational differential between the center of the Earth and the sides. And if this doesn't make sense, there is a video that explains it more. You really don't need to know it in detail. The only thing you do need to know is that the bulge is elongated and it's towards the moon. And so here's a video. It kind of goes into some in-depth. If you're really interested in tides and how tides work, this is the video to take a look at. So there are two types of tides. There's a tide that's caused by the moon, but there's also a tide caused by the sun. Because the sun is also pulling on the Earth, and the Earth is pulling on the sun. So 2/3 of the tides are caused by the moon, 1/3 of the tides is caused by the sun, and so the two types are spring tides and neap tides. So spring tides are when the solar and lunar tides are aligned, and they're big tides. So they happen during a new moon and a full moon. So during these times, the tides are bigger. And so you can see here, there's a solar bulge and a lunar bulge from the tides. And those bulges that are pulling out are lining up. And kind of like constructive interference, they're going to add together to make a bigger tidal bulge. And that happens when the moon is pulling in one direction and the sun is pulling in the same direction. This is what happens. Neap tides are when the solar and lunar tides are orthogonal to each other, or they're at right angles. And they're smaller because the tides are partially canceling each other out. So this happens during the quarter moons. So when we have a quarter moon and the moon is over here or over here, we get a tidal bulge from the moon this way, and we have a solar tidal bulge pulling this way, and they're going to partially cancel each other out, kind of like destructive interference. And so they make weaker tides. And so this explains why sometimes we have like high tide and low tide. We'll have a really big high tide and a really low tide. Those would be during the spring tides. And I always remember neap tides are weak tides. They kind of rhyme, neap and weak. They don't really rhyme, but kind of rhyme. Neap and weak. And so during weak tides or neap tides, the high tides are not very high and the low tides aren't very low. We don't get very big swings. The swings in tides are very small. Here is a video with Neil deGrasse Tyson talking about the tides. I'm not going to play it here. I do encourage you to go to the Google Slides and take a look at it. He answers some very interesting questions and he explains things very well. So do take a look at that. It's kind of interesting. And that is where we're going to wrap up. Thank you guys, and I will see you guys soon.